I'll be talking about the work that we've been doing to make sure that big data open source software runs smoothly and effectively on Google Cloud Platform. Now, I want to begin with the big questions underlying all of this, which are what exactly it means to run big data open source software on Google's cloud, and secondly, why that matters to you. Now, imagine you have an awesome idea for a web application. Maybe you've been talking about it for some time over lunch, and you decide to go for it. You code it up over a weekend, and you hit the launch button. Well, as it turns out, the rest of the world thinks you're onto something. So, somebody posts an article to Reddit, a Slashdot article appears, and before you know it, you have 1 million new users overnight. So what happens? Well, all too often, the story ends right there. Your server melts, and your users quickly lose interest in your service unavailable site. But let's hit the undo button. Suppose you went with Google App Engine, and your app scaled seamlessly just like you intended. So now you have 1 million happy new users. So what's the next step? Well, as it turns out, life likes to throw curveballs at you. So you see bots and spammers show up, flooding your forums with junk and driving your users away. Now, when you only had like 10 users, it was pretty easy to just eyeball the logs and ban a couple IP addresses and be done with it, right? But somehow, as it turns out, eyeballs just don't scale to 1 million users. And your computer now refuses to load the terabytes of log files that you now have. So you might find yourself reinventing the wheel. You might write a quick program just to process those logs automatically, try to catch these spammers. Maybe you'll find you need to run on multiple machines, so you'll write a controller program to automate this, right? So what began with a day's worth of work quickly ends up with you just discovering a week's worth of work. And a week later, you're a month behind, and in the meantime, your website has become a lost cause. Well, let's hit the undo button again. What if you didn't have to reinvent the wheel? What if, with just the click of a button, you had all the tools you need to solve your spam problem before lunch, and you could spend the rest of the day building the next killer app, building the next feature for the next 10 million users? What if you really could scale from a garage size to Google data center sized overnight? As it turns out, that's exactly what running open source big data software on Google's cloud is all about. Now, just to get into some of the mechanics here of actually running on Google's cloud, there are two big pieces to this puzzle. On the one hand, we have making the most of Google's infrastructure offerings. Now, traditionally, if you've invested heavily upfront in a lot of hardware, you'll end up with all these machines of a certain size, a fixed shape. And all too commonly, you'll find yourself wasting endless time and money building the software to try to fit this mold, trying to fit them into this fixed shape. In cloud, we turn this upside down. So you should write your software however it feels natural, write your software for your application logic, and then get the resources that match your use case perfectly. Perhaps the most egregious example of a fixed shape would be when you buy hardware, the time dimension is extremely rigid. You end up with this contiguous block of time for your on-premise hardware that is unbroken between the time you buy it and the time you're ready to throw it away. Well, in cloud, why not just get multiple disposable clusters instead, right? If you need to get some data analytics done today, why not run multiple clusters? Each analyst gets their own cluster to use by themselves and get your workload done now instead of having to wait in line. The second piece of the puzzle is making the most of Google's platform rather than necessarily just having to duct tape a bunch of little components together. And this is where we've been doing work to make sure that you have all the tools and libraries necessary to make it one seamless experience. We want you to be able to use your open source tools as well as higher value Google services like BigQuery and mix and match and have them interoperate seamlessly on the same data. And just to give an idea of what this looks like at a very high level view, let's go to the demo machine. I'll explain a little more about what's happening here under the hood, but just to see what it looks like, I'm going to go ahead and deploy an 88-core cluster that's fully loaded with all the greatest data analytics open source software there is, and see how many. Sorry, I should actually type a command. Yeah, let's do that. And we'll see what happens a little bit later. So let's go back to the slides now. So you might have noticed Hadoop was at in the title of the last slide. And we really are talking about all big data open source software here. But just to give a little bit of Hadoop, a little bit of Hadoop context, Hadoop has played a crucial role at being one of the very first open source implementations of the MapReduce paradigm, and one of the first such widely adopted software frameworks, which ultimately provided this fault tolerance and the machinery necessary to provide a really low barrier entry to starting to make use of large distributed clusters of commodity hardware. And this is really what enabled big data to really go mainstream and help it mature to what it is today. More recently, we see Hadoop serving in a crucial capacity as a point of convergence. So what I mean by this is not quite sitting down to write RFCs, but what we have is some organic community consensus-driven convergence onto certain behaviors and certain interfaces that came out of Hadoop. And one specific example of this is the Hadoop distributed file system, where we see that as data and analytics grows, as the ecosystem grows with a diverse set of tools, all of these tools are able to promise interoperability with your data simply by virtue of implementing the Hadoop distributed file system. And that brings us to one product that we have today available and available for you to use now, which is the Google Cloud Storage connector for Hadoop. This is built on top of the aforementioned standardization by implementing the Hadoop file system interface. So what this allows is for you to install this connector onto your Hadoop clusters and to replace at least a portion or all of your data access needs using Google Cloud Storage instead of Hadoop HDFS. We provide tools for automatically installing and configuring this such that you can either run in a hybrid mode so that naturally you can take your time migrating what data makes sense to put on Google Cloud Storage together with HDFS, or for new batch workloads, it might make sense just to run without any HDFS altogether. And we have screenshots, but let's go to the demo machine. So live is always better. So let's go ahead and we have a Hadoop cluster open here with the GCS connector installed. So what we'll see here is, let's just create a file. Let's echo here. We'll just say hi to cloud and create hello.txt. So we can see, this file has been created on my local laptop, and we can go over here to Google Cloud Console and, nope, not a new folder. We want to upload this hello file through our familiar GUI interface. And as we can see, so this is the cloud portion. Everything worked just as we intended. And now what we can do is we find that we have the Hadoop file system shell is available in this Hadoop cluster, and we can just cat out that exact same file. I think I mistyped something here. And we see that we can access that same file the same way we would through the Hadoop file system shell, as we would through the GCS GUI, as we would through the GCS command line tool, gsutil. So let's return to the slides. So to summarize what we've seen, we have two axes of interoperability here. On the one hand, we have cloud interoperability, where we have the same access and the same behavior from all different cloud services. Importantly, this also means the same access for other Google Cloud services like BigQuery, which can interoperate by sharing GCS as the common data storage. The second axis is Hadoop interoperability, as we talked about, where we can unlock a really broad range of open source tools just by virtue of implementing this standard Hadoop file system interface. And that includes making GCS work with Pig, Hive, Spark, Shark, and numerous other open source technologies. What this ultimately means for you is a significant reduction in operational overhead, because now your data is not tied to any single location in terms of some set of disks, nor is it tied to any particular technological stack. So if you're tired of MapReduce and you want to try something new, your data is still there. You can start processing it in a new framework. Now, when the question arises of whether something like GCS can really be a feasible replacement for HDFS, performance often comes up. And I think there's really two real aspects to this question. First is the question of whether the networking technology is really progressing in the right direction, such that doing this would be feasible. And secondly, there's this question of relinquishing a little bit of that fine-grained control that you might otherwise have with HDFS, like little things like rack locality or replication policies. And I'm reminded of the first time I actually had an opportunity to write a lot of assembly code. I remember I was really excited going into it because it was this opportunity to try out all the clever hacks I always wanted to make it run fast. And it turns out, after the novelty wore off, it was actually fairly painful writing all this assembly code. But I do remember, after so many hours of muttering at the screen, getting it to finally work the way I wanted and getting a huge success. It was like 20% speed up. I later found out, sadly, that if only I had flipped the -03 flag on GCC, the original program already would have ran twice as fast. Now, what I learned, aside from the fact that maybe I'm not the assembly guru I had hoped I was I learned to trust the compiler. I learned to trust the decades of experience, of expertise from compiler experts that have gone into it. Whenever Java happens to be the right tool, I feel rest assured knowing that my memory management is actually in pretty good hands. And when I use Google Cloud Storage, I know I'm taking advantage of an incredible amount of research and development that has gone into Google's storage technologies over the years. And Google Cloud Storage still might not be the right tool for every use case. But what's important is simply having the option to take a step back, let somebody else handle all the dirty, grungy work, because that's ultimately how you can let magic happen while you focus on building the features and products that you actually care about. Now, that said, earlier this year, the technology consulting company Accenture actually released a study of the performance characteristics and total cost of ownership trade-off between on-premise deployments of Hadoop as compared to Hadoop on Google Cloud. And I'd encourage anybody interested to read the whole paper. It's quite in-depth with a lot of different dimensions of analysis. But what we have here is at least one sample out of that paper showing a realistic real-world workload where we have the red bars here showing a mixed data flow model where we use the GCS connector for the input and output of the initial and final stages of the MapReduce, still using HDFS as an intermediate store, as compared to the blue bars, which are just using local disk HDFS. And we see that we actually had a pretty encouraging speed up using the GCS-based, the GCS connector-based data flow model. The green line here at the top is the benchmark value of the bare metal Hadoop deployments from a total cost of ownership analysis. And we can see that across all dimensions, the cloud deployments outperformed. So lower values are better here. So I'm happy to announce that we've also been working on two other Hadoop connectors for connecting to Google Cloud Services. We hope that the Datastore connector will help you bring data analytics through open source tools to operate on the same data that you use in your web serving or that you generate. And we hope that the BigQuery connector will help aid the seamless interoperability between whether you started out just using BigQuery and want to use open source tools, or if you started out with open source tools and want to start using BigQuery, you should be able to go either way seamlessly. Both of these we hope to make available publicly in early April. Along with all these connectors, we also have a thin helper tool called BDutil, which helps deploy and install all this Hadoop software with a thin extensibility mechanism for customizing your software and mixing in more open source tools. And that brings us to what we'll demo here using BDutil of Shark on Google Cloud Platform. Now, Shark is a prime example of how all this open source technology works together and works well with Google's cloud. Shark is ultimately, is basically Hive on Spark, where Hive is SQL on Hadoop. So the Hive engine will translate SQL over unstructured data into MapReduces that run in Hadoop, whereas Spark is an entirely different data processing model than MapReduce. But here we have Shark implementing total compatibility with Hive queries, but instead of using MapReduces under the hood, it will use Spark. And we'll see how this plugs into Google Cloud Platform in two ways. First, by reading your external data from GCS so that your data can persist independently of persisting your compute cluster. And secondly, by plugging into Cloud SQL so that you can have multiple different clusters all plugged into Cloud SQL as your metadata store and reading from that. So we'll go to the demo machine now. And we see that, first let's launch a cluster. Let's see, BDutil. We ran something similar to this already, but just to elaborate a little bit, what we have here is an extension that I've created here that's just for installing Shark on Cloud SQL. And all it does is here are some shell scripts that actually install Shark. We'll provide some cluster-specific configuration, and we just kick it off. If we take a look at our cluster-specific configuration here, we see that we just have some basic settings like number of workers, a prefix for the cluster name that all our instances will have, which project to use, and so on. Since we were lucky enough to kick off a cluster a few moments ago in this presentation, we can go ahead and just use that as our other cluster. Take a look inside. So, we'll run as Hadoop. And let's go ahead and boot up a Shark command line, a Hive command line, and maybe another Hive command line on the second cluster. Clear all these out here. So we can see we don't have any tables yet. Now, we can go ahead. I happen to have a data set here of, let's see, a natality birth data set for the year 1970 through today. And it happens to be an Avro format. So this is just some files sitting in GCS. And what we'll do is we'll create an external table which is pointed at that. So now that that has been created, we see that it appears in both Shark and in Hive on the same cluster, and in Hive on the other cluster. So you can see, this is demo 2 down here and demo 1 up here. And sure enough, we can also select top 10 from it from any of these 3 shells. So suppose we want to find out if there are any trends in the number of underweight births as a fraction of the total number of births over the years. So here's a query that we have prepared here, and we'll just plug it into Shark. Now, while that kicks off, suppose we also have another set of data. Here's a common use case. Suppose we have a bunch of files in JSON format. So people often use JSON format as an initial data format, but it's usually good to get a binary format like Avro. So we can go ahead and create this JSON table in our second cluster. And then what we'll do is, let's see. We'll use Hive as our data conversion engine here, simply by creating a second table in Avro format, and then just saying select star out of our JSON table and writing it into our Avro table instead. And we'll do that in our second cluster. And now we can take a look at the web UIs here. So here I have a web UI open of the built-in Spark GUI. And we can see that we see all the commands that we just ran. We ran select, and it looks like it's already finished, the Shark query that we kicked off a little while ago. And if we go into our second cluster, demo 2, and open the Hadoop console, we can see that Hive has gone ahead and translated that second query, that JSON creation query, into a MapReduce. So now we have MapReduce running on this, some data that's in GCS, right next to Shark running against Spark on other data that was also in GCS. And we can see that, oh, sure enough, we got the results. We see that over the 80s, the percentage of underweight births went down a little bit, and then seemed to go up as we came out of less prosperous years, apparently. So some very interesting data.